Uh, okay, so we'll just pick up where we left off last week, which was basically introduction to what theoretical physics was and a bit into the electrodynamic theory and what a Lagrangian is. And we finally ended off with a question that Rahul posed, which was how would electrodynamics look, or even if it would exist in any even dimensional condition or space. Okay, so we can start off with uh, giving a good idea on what a Lagrangian would be and how we start to define Lagrangians. So usually when we start in theories, uh, since electrodynamics is a relatively simple theory, but in general, when we're talking about theories where we don't have a lot of information uh, at hand initially, we can start off by building Lagrangians by looking at the system and sort of seeing what stays consistent when we change a few variables in the system. So looking at the system and seeing how it is invariant to some sort of change will give us a clue on the structure of the Lagrangian. Or at least that is a good place to begin. So, okay, so, and obviously Lagrangian is, a Lagrangian is, we can say it's a mapping from uh, velocity space to real numbers. What velocity space is, it is a space of this. So where q and q dot, excuse the, yeah. So q here would be the set of coordinates that we choose to describe a certain phenomenon, and q dot is its time derivative. And a function from this space, let's say L, to real numbers is what is mathematically a Lagrangian. So all this is saying is it is taking inputs as q dot and q and giving out a real number quantity. Okay, so why is this quantity even important to discuss, or like why is it important to talk about in terms of theoretical physics as a whole? Is it's basically because this quantity contains information about the entire system. So the entire process can be extracted from this one quantity most of the time. So that's why Lagrangian, even in the first place, is, we try to find Lagrangians. And once we have a Lagrangian, we can do a lot of things with it. Like so obviously once we have a Lagrangian, we can find out the field equations of that theory. So that's the direct, the first thing one would do once you construct a Lagrangian. And you can also, depending on the sort of system, and if you say that, okay, well, if you just say depending on a sort of system, you can do certain things to Lagrangian, which will give you relevant results. Without getting too into the specifics, that's just the picture of why Lagrangian is important. Okay, so well, now we can start to discuss about Rahul's question, keeping this Lagrangian topic in mind.
Before we start talking about that question, I guess I had another question that, for the sake of this episode, we can leave it for some other episode. But why should the Lagrangian be dependent only on position and its first derivative? Is something that we can possibly go into in the future, but yeah.
Okay, well, we have to think for that. Let's see.
Oh, well, yeah, go on. Yeah.
The codomain is obvious. Well, we do want a function which is real. So the codomain R would be a good construction. And why did we choose Q and Q dot? Okay. So in a sort of way, it's in a if you put it simply, it's convenient. What I mean is, first of all, it would be easy to represent a quantity in terms of Q and Q dot, because once we know Q, it's easy to compute Q dot, and sort of you can put it up well. And not only that, so we have another quantity, right, called the Hamiltonian, which is in the phase space, which is the position and momentum.
Right.
And they have a very good conversion, sort of going from the phase space to velocity space.
Right. That's all fine.
It's actually it's a sort of natural transformation that comes.
Correct. Yeah, which is the Legendre transformation.
Exactly.
But
so, yeah.
I guess the question would be, why is that the entire dynamic information of the system is captured by only these two variables? Why not
sure.
Double derivative.
Second, third, higher order derivatives, or even time, which actually it may be dependent on time, but for the sake of simplicity, we are just ignoring that, I guess. But why that? And I guess my physicist brain is telling me that it's because this Lagrangian, how it's initially constructed, is just a difference of kinetic and potential energies. And since the kinetic energy is essentially the Q dot term where that comes from, and the potential energy is dependent on position. So, and through energy conservation laws, we can find everything. Maybe that is the
answer.
The answer, maybe.
That sounds like a very good sort of analogy between the two.
Right. But could we have systems where we have higher order derivatives?
Higher order too. Yeah.
Anyway,
Right. If you have like double derivative, that would correspond to force, right? In a way, it's acceleration and the force. So if a force is acting on the system, why do we not really use that information?
Okay. So we have to sort of go into another concept, I think, for when we're talking about force. The forces will come into play when we talk about Euler-Lagrange equations.
Right.
Lagrange equations. Right.
And
actually, force is actually captured by potential energy term in a sense. Right?
It's a divergence of the potential or something, right? That's So So well, we say it's not a part of the Lagrangian itself. Okay, so the question is why it itself isn't a part of the Lagrangian, right? Okay.
Yeah, that's the second derivative of Q.
Exactly. Let's see.
I mean, for the sake, I think it'll be better if we discuss this when we go into our Lagrangian video. But this can be an open question for now for the viewers. But you can go on.
So one last thing, I would just like to add, like the same question of Rahul, like why Q and Q dot? As you said, it's momentum and the kinetic energy and potential energy, the simplest construction of the Lagrangian.
Right.
One other thing I could think of is, so see, the whole reason we're talking about Lagrangian is to talk about the system as a whole.
Right.
So when we talk about system as a whole, we are obviously talking about coordinates, so like how things move in a system.
Right.
So coordinates change, and or how the coordinates change.
Right.
I mean, not coordinates change, sorry. How, or like basically coordinates.
The system moves in coordinates.
Right. And the time derivative, why? Because how it progresses in time.
Right.
So basically it's so it would be like saying I'm talking about the system, the present state of the system, and how the system changes with time.
Right.
So we have Q and Q dot in a rough sort of sense.
Right.
Describe the Lagrangian, and this would
Perfect.
So anyway, we can discuss about all the other interesting questions like Charu's in the Lagrangian video itself. We can get all that clear there. So anyway, moving forward, so we'll talk about Rahul's question for now. So we'll start with that. His question was, would you like to just ask it again?
So I guess my question in the previous video was, what would electromagnetism look like in even dimensions? Because we saw that there was something innately odd about the electric and the magnetic fields coming together in three-dimensional space. Yeah.
Okay. So okay. So if I would start this discussion, then again I would start off with at least going in the direction of Lagrangians again.
Right.
So there is a Lagrangian for electrodynamics, and a sort of a sort of important part of a Lagrangian, as we will see in the video that we will say, is called the curvature. This curvature, we can sort of represent Lagrangian as an exterior product of the curvature and another entity. So this other entity is nothing but the curvature, but under an operation called the Hodge operation, star operation, or whatever you might know. Yeah. So the exterior product of these two will give you the total form, volume form in that space, which is it's a way of representing the Lagrangian. So when we are looking at the question that Rahul asked, it would, I would sort of try to start off this question by looking at curvature.
So why does the curvature and its Hodge product with Wedge product with Hodge star curvature represent Lagrangian?
That is actually another whole, that question itself could be an entire video, because like its behavior and sort of thing. What you can say in a completely logical senses, so a curvature is a two form, and the Hodge of that is the whatever the dimension of the space is, it's n-2 form. Right. So when you do the wedge, you get a n form, volume form, right? And you're taking the volume form to real numbers. So in a sense, well, you can say that the volume form has all the coordinates, right, in it itself. So in a sort of sense, you're getting all the information about the system.
Okay.
So in a very rough sort of sense, there is a completely proper derivation of why it's like this and stuff, but that would be another video itself. It would take too long if we go into that.
Okay.
But we will cover it eventually.
Yeah.
Yeah.
So in a rough sense, it's that's the reason. So I would sort of think that if we go through a curvature direction, it would be we could start off like that. So here, so for the regular electrodynamics, the classical one, the curvature, I'll represent it as F here. So F is B, which is a two form, as we discussed last time, plus E, which is again one form, and a dt.
So
yeah.
Just one more question about the curvature. If you take any entity and its wedge with its Hodge, that will give us the volume. So why only curvature?
So again, because see this it would come in the derivation itself. Why only the curvature? But because the curvature has a few important it has a few properties which are very important when we're looking at the system as a whole. So well, we know that the covariant derivative of curvature is always zero, or yeah, it is, right?
Yeah.
Yeah, I think it. Yeah. So I mean, there are some properties of the curvature which are sort of only specific to curvature, which when you build up on the when you try to derive the Lagrangian from curvature, it all adds up and comes well. Does that make sense? If you take any two form and take the Hodge and you take the wedge between the two and you do it, you won't get a Lagrangian. But to go into the details of the question you asked, it's better if you answer the question in the derivation video. It will be clear there. I'm not really able to answer the question to a proper extent right now.
I think we can have it with the derivation. That will give a good intuition.
Right. So anyway.
Also, sorry. The covariant derivative of curvature is not always 0.
Yeah, it's not always. It's for the connection, right?
Connection. Yeah.
Right.
If it's a Levi-Civita connection, it's 0, is it? Or,
no, it's all connections.
All connections, right? Yeah. Exactly.
Yeah. So, I mean, there are some properties. I'm not able to remember them right now, but there are a lot of properties which allow the curvature itself to, because sort of we can say that the curvature, right, it's built off of the one forms connections. So it would be the exterior derivative of the connection plus like a hat a. There's a formula for the curvature, and when we take the star of that and then we do a wedge product, and we'll basically see it unravel, and we can see the different forms and stuff. Anyway, so this is the curvature. Sorry, this is the curvature for our Lagrangian. Curvature for our electrodynamics. That is, it's a standard curvature. It's well defined and sort of stuff like that. So here B
happens to be the force, but
yeah. So this is the magnetic field. This is the electric field with this exterior product with dt.
Yeah.
Okay. So, well, now again, this is two-dimensional. Sorry, a two form. This is a one form, and this is a one form. So the whole thing is a two form in R4 or in a four-dimensional space. B is a two form in R3. E is a one form in R3, and this F quantity is an R4 because of the extra T dimension. Does that make sense? Okay. So, well, Rahul's question is, what if it was in even dimensions? So basically, we are saying B is some form in R4, and this F quantity or the entire quantity with the time would be in odd dimensional space. Does that make sense?
Let's say, yeah.
Right? Okay.
It's not making sense to me.
It's not?
I know. So in four dimension, is again two form. So then E wedge dt, you're saying that's why it's odd.
No,
not really. So we started out with saying that in space, B is two form and E is a one form. When we say space, it's R3, three-dimensional space.
Oh, okay.
But time is your fourth dimension. So that's how it becomes R4.
R4.
So your E wedge dt term is now a two form. And your B is also two form. But now, if we go to even dimensions in space, that means including time, we have an odd dimension again.
Oh, okay.
Right. Okay. So yeah, take it away.
Exactly. Yeah. So just for simplicity's sake, we'll just take it as R. So all the dimensions we're talking about is just R. We don't have to go to M or anything. So okay. So well, now we have to define B and E in an even dimensional space. And we have to sort of construct the same Lagrangian, same form of Lagrangian, same form of curvature. I mean, that would be the first step, at least. We can definitely come up with some new definitions of magnetic field, electric field, curvature, and all that stuff. We can always come up with it, but for now, let's just go with the standard structure of the already working R4. So now we have to talk about, basically I'll write the question here. So how do we define B and E in R4? So this is the question now. So well, logically what I can say is, if I define B as let's say as a 3 form and E as a 1 form, then we can get us we can construct the same curvature. Does that make sense?
Yeah.
I'm just slightly extending the definitions for B and E by just 1 form.
Okay.
So yeah, because yeah.
So, but in 3 dimension, B was 2 form, then E with dt was also 2 form, so F was a 2 form. But here, if you're taking B as 3 form and E as 1 form, then E with dt will be a 2 form.
Will be a 3 form. Oh, no, E is a 2 form. So,
okay.
Yeah, E is a 2 form. I'm sorry. So
Yeah,
B
E
is
is
a
a
3
2 form.
and E is a 2 form. The 1 form difference.
Okay.
And yeah, as you said, when we take B plus E had dt, it would be a 3 form now. So curvature is not 3 form, it is only 2 form. So one way that I can think of defining, again, I want to preserve the structure. So what I thought is, instead of defining F as B plus E hat dt, we'll define star F as B plus E hat dt. Because star F can be any dimensions. Just F has to be 2. So in this case, star F will be 3 because we are in 5D, R5.
R5, right, including type.
So we'll define star F, right? So we'll define star F as same thing, B plus at dt. Yeah.
But now this should be consistent with all our starring operations, which it will.
Yeah, it will. So just move this one. Yeah. So does this make sense, what I did?
Yes.
Yeah.
You might get a lot of questions in your mind, like, if you define star F like this, then how will F be? Or will that F had star F, will it still be the same? Or like so many questions. But well, if you have any questions like that, then we can always discuss it right now. Is it there or is it all clear?
I guess when you star of F, you need to get back F. Right. So that way we can maybe find out F if that's what we're doing.
Right. So since this is a 4, it has 1 time dimension, right? Which is, so it is plus, 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 minus.
Right.
So because of the way we have formed the metric,
we have a minus.
R5,
yeah.
Star can never be 1. It's always -1.
Right. Exactly. Correct.
Right. So when we're defining the Lagrangian, we can always just put a minus sign in front of the entire quantity, which will make it consistent with the 4D regular electrodynamics itself.
Right. So there's secret -1 to the power n, where n is the number of dimensions.
No, actually, because in this sort of in this metric, it's always negative. There's only 1 negative. So no matter how much we extend the dimensions, keeping that only 1 negative, the star square will always be -1. So
right. Okay.
With star 5, R6, anything, it'll always be -1 itself.
Right.
So the Lagrangian will just have an extra minus sign on it. In any case, any dimensional case.
Correct.
Okay. So well, basically we have now defined star F, and we can compute F also, which would basically be so if we star this star F itself, basically that's what I'm saying. So we get minus F, right? So we get minus F is star B plus star E hat B. There is no real need to compute this because I mean, you can if you want as an exercise, but you'll not get any interesting results. Maybe you can sort of expand this bracket here. But yeah, whatever. Like it would just be it would be a good exercise, but we would really get nothing useful. And now what we do to construct the Lagrangian is obviously we do f hat star f. And since f is a two form, so like f hat anything is anything hat f. Like we can switch the two things. So we can just construct the Lagrangian as let's say L is this would be just minus star f. Does this make sense?
Yeah.
And the action would obviously be integral over this.
But it will it will depend on the dimension of the space, right? If we can do this or not.
No, it will depend on the dimension of the forms that we're taking. So
in all cases, we can still do this. So
yeah.
there will always be a distinction between magnetic and electric fields.
No, I mean, you mean the f hat, like the switching of the f's, right?
Yeah.
Oh,
right. So,
right.
So like there's this, it's like a hat b is I think minus one to the power pq, where pq are the forms of this times b hat b cross a. I'll call cross for now. So in this it's always even, so that's why we can always write it like this.
Oh yeah, right.
It's just from the antisymmetry of differential form.
So and again we can obviously construct the action from this and so on. So in this way we have constructed a Lagrangian for even Rahul's case. And if we compute the field equations, we will get some field equations, and it might be the same, or it could not be the same. I can't really tell. But since we have constructed it the same way, it should be the same way. At least we can say that the first two equations, if you guys remember, which was dE and dB, they were both zero, right? So that will be the case here also, just from the basic construction itself. And actually, we can go a bit deeper into that. It's because, like, since if we take any dimensional R cases, the first two equations will always be the same, because of a special property of R4 that it's a contractible manifold.
Right.
So when we talk about contractible manifolds, we can say that it's going a bit deep, but technically we can say that all the cohomology classes are all trivial. They're all zero. So any form that you take is always exact, which would mean D of that exact form is always zero.
Oh, okay.
Right. So,
but the interesting question then becomes, what if the genus is non-trivial of the space? What if it's not contractible?
Then we wouldn't get any we can't tell anything. We have to actually compute it to find the property. But for any contractible, or let's just say for R4 for now, the first two equations will always be in the same form, no matter how we.
And for the viewers who may not have heard of contractible, it's just that you can shrink the whole space down to a point.
Yeah.
But let's say you have something like a torus or a donut, you can't shrink it down to a single point. So it's not contractible. Yeah.
So that was for I think we can conclude that discussion. We can obviously extend it to any manifold instead of just R, but it would essentially be the same. The construction will be the same process.
Right.
We cannot just logically think of how the field equations would be as we did in our case.
Right.
But the construction would be the same. And if anybody would want to go and really see how it would be, then you can always do it. It's a good exercise to do that. It's just a bit of calculation and things like that. So, so this, you're saying?
Yeah, and I guess this is one of the ways in which you can see how abstraction may be useful, where you're pushing the boundaries of the theory,
Right.
quite literally sometimes. Yeah. So yeah, if your space is not contractible, you have some non-trivial physics that's coming into picture that can only be seen through abstraction. But anyway, yeah, go on.
So yeah, so this was the, I mean, this was to answer Rahul's question, obviously. And the only respectable answer I can tell you is that the first two equations will be the same in even dimensions. I
Right.
don't know about the odd dimensions. We have to
Right.
see. But
Yeah.
yeah, well, so this was the sort of, this is the way to take a theory and to extend it, to remove the conditions, like instead of saying 4 dimensions, n dimensions, or instead of saying R, M, a random manifold, and so on. We can construct the theories in a systematic, we can sort of extend the theory systematically, just like this, to the highest, most abstract level. So in this case, it would be where it is n dimensional, a manifold M, which is n dimensional.
Right.
So that would be the most abstract conditions. And from there, we can obviously derive all the field equations and see how it will be.
Right.
So this is, so the picture that I wanted to paint is sort of the thought process behind abstracting theories. And
Right.
how, yeah, once we've decided which points to abstract, we can build the theory on that. Does that make sense?
Right.
This
But
was
yeah, go on, Charu.
this was actually very nice to think of that curvature's form should be preserved. It should be a two form, and then so how do we go about defining it? So yeah, it was really nice. We can take Hodge of it and define that
Right.
instead of curvature. Yeah.
Right. And so there is also this connection that you see through this abstraction that one, there is some requirement that the force has to be a two form, right? But this forces the magnetic and electric fields to be two different forms and not of the same
Yeah.
level, whatever, of the form, and how this connection arises. So this is a very deep connection here. Um, and yeah, we could only see it through abstraction. Otherwise, our question of why are they fundamentally different
Right.
won't be answered, at least
Yeah.
mathematically. Yeah. At least physically, we have some intuition for it. But I guess this is the mathematical justification for that intuition. So
Yeah.
that's a beautiful thing. Yeah.
Yeah, it's a great observation.
Yeah.
So yeah, as you go and do this in many more theories, we would see a lot more beautiful relations and sort of mathematically, why it must be like this.
Right.
Reasons, as Rahul said, and they're just amazing if you really go and do it. So well,
Right.
this was basically to like it should be a reason to abstract things, to see the beautifulness between B and E and other things, everything actually. So, if we abstract something enough, then we might, just, if I'm like speaking in the cloud, like, we can actually just see connections between everything. So everything
Right.
is, in some sense, is a reason that it's like this, it's like that. It has to be.
Right.
Well, I feel like mathematical physics is the final goal, I think, is to sort of explain everything using one thing.
Yeah.
Or sort of we derive why something has to be like this.
Right. That's
So
right.
that's the power of abstraction and mathematical physics and so on. So
Perfect. Yeah. So yeah, I guess this sets up the stage for all our future talks. And yeah, we'll plan to meet once every 2 weeks and release videos then. Yeah, if anyone's watching this, please feel free to comment and connect with us. it'll be really nice.